Welcome to the Wire Reinforcement Institute's Continuing Education Program course CEP2, titled Welded Wire Reinforcement, Usage in Tilt-Up Wall Panel Design. My name is Paul Aubie, and I am the Technical Consultant for the WRI. I will be presenting today's content. Some quick bookkeeping. You can receive continuing education credit for this course by successfully passing an end-of-course quiz. The link for the quiz is included in the video description below. Note too that the attendee will be required to provide an attendance confirmation and will need to complete a course questionnaire, both of which are accessible upon achieving a passing score on the quiz. Today's course is broken into 8 segments related to welded wire reinforcement usage in tilt-up wall panels. We will start with the material specification and design code, so we'll get into ASTM and ACI. We'll then get into tilt-up wall panel design basics, not necessarily specific to welded wire reinforcement, just as kind of a primer. And we'll jump into why welded wire reinforcement. Why is that a viable option for tilt-up wall panels? We'll have a brief discussion on high-strength reinforcement, so comparing 60 KSI and 80 KSI reinforcement. And then we'll go through a step-by-step wall panel design example. From there, we're going to discuss information that the design professional of record should include on their contract documents, and that will segue into a discussion about submittals and conversion calculations that the engineer and contractor will have access to during the submittal process. We'll then wrap up with some photos and some brief discussion related to work on the job site. So first, we start with a brief discussion of the material specification itself. Welded wire reinforcement is found in ASTM A1064, and it is defined as a material composed of cold worked, deformed, or plain steel wire that is cold drawn or cold rolled from hot rolled steel rod. It goes on to say that longitudinal and transverse wires shall be securely connected at every intersection by a process of electrical resistance welding, which employs the principle of fusion combined with pressure. So keep in mind that electrical resistance welding, there is no preheating of the weld site, nor is there depositing of a consumable electrode. There is no flux, no inert gas being used. So AWSD 1.4 does not apply. The best way to think about it is that your starting material, which is the 90-degree intersection between wires, is your finishing material. There is no additional electrode material being deposited. In a nutshell, the process of welded wire reinforcement manufacture is illustrated right here. We've shown it kind of in 4 steps. We start with the hot rolled rod. That is then cold worked using rollers or dies into a final design wire size, which is shown there kind of in the blue rectangle. These wires are then automatically assembled, arranged, and they are ultimately fed into the machine welder, which is shown in the yellow or orange rectangle there. The machine welder, as you can see, is comprised of rows of welding heads that fuse wire intersections together by completing a path of electrical current through the wires. Now, depending on the project, these machine welded mats can then be moved downstream to a hydraulic bender for those project applications requiring bent material. So that bender is shown there in the green rectangle. So again, in a nutshell, we go from hot rolled rod, go through a cold working process, then a machine welding process, and then ultimately for bent material, we go through bending fabrication. Here's another view of a machine welder in action. Notice that the welding heads are programmed to selectively fire to suit the welded wire mat the mat arrangement itself, so you can actually see those electrodes which are firing and those that aren't. The ones that aren't obviously do not have a wire intersection aligned with them. The image on the right is kind of a schematic diagram of the electrodes, which are shown in yellow, contacting the wire intersection from above and below. Current is then passed through the wires to fuse them together. The process of creating a welded intersection is essentially instantaneous, so this is it's not taking any longer than half a second or so. Also noted here are some welded wire reinforcement attributes that are relevant to the designer. So I think one of the most surprising things to designers is that wire reinforcement is available in sizes up to about the same size as number 5 rebar. Commonly produced with diameters up to 0.628 inches. Yield strength, again, commonly available in 80 KSI. The reference yield strength for deformed welded wire reinforcement is actually 70 KSI. 80 KSI is very commonly produced and utilized. And also note that we're not really talking necessarily about stock material here. The way the equipment works in current times, it's sophisticated enough to produce very customized mats very quickly. So you can have variable wire sizes, spacings, wire lengths in both directions on the mat on a common mat. So that customization is key to acknowledge here. For the code aspect of welded wire reinforcement usage, ACI 318 is the standard we focus on. It's important to keep in mind that welded wire reinforcement is a mild steel reinforcement that behaves a lot like rebar. We use the identical design equations and routines to derive steel areas for flexural, axial, and shear strength. Keep in mind too that the presence of the welded intersection, it doesn't change our sectional strength calculations that we carry out as designers. Perhaps the most familiar comparison to make here would be ASTM A615 rebar. Also worth mentioning is that the code does allow for intentionally positioned welded intersections to be relied upon to reduce development length and tension lap splice length. This provision is typically not utilized in tilt-up wall panel design, and instead the wires on the mat are simply lapped using the same equations one would use for loose individual pieces of rebar. But it is worth noting that those welded intersections, when located properly and of a certain size and frequency, can be counted on for structural purposes. As we move into panel design, there are some basic considerations that need to be made. So as a designer, in designing a wall panel, you're capturing the effects of out-of-plane loads, so applied wind and seismic forces that are normal to the wall plane, as well as the rotational effect of applied roof and floor loads that might arise from having an eccentricity from the center line of the wall. Effects of in-plane loads, of course, we have axial force due to the self-weight of the wall, we have axial force due to applied roof and floor loads, and then wind and seismic forces, essentially shear wall behavior. Volumetric change is another thing, so thermal expansion is a pretty significant consideration, along with the restraint effects. How are panels connected together? What does that connectivity look like at the corners? So volumetric change is something that we do need to pay attention to as designers of tilt-up wall panels. Boundary condition assumptions. So roofs and elevated floors resist out-of-plane translation. Slabs on ground resist out-of-plane translation. And foundations resist out-of-plane and in-plane translation, plus in-plane shear wall overturning when that is applicable to a certain panel. There is, of course, a beneficial effect of coupling walls together at jams, so there's a connectivity there that can occur that you can get some benefit out of wall panels that are aligned in a row from a stability standpoint. And then, there is a pretty significant focus on mechanical connectivity of the panel at the foundation, at the slab on ground, elevated floors, and the roof. Last but definitely not least, and a pretty heavy focus of this presentation is slenderness effects. So we're talking about panel height to thickness. Wall slenderness can of course impact P delta effect, which can have a magnifying impact on both the flexural demand and of course the deflection of the wall panel itself. So we'll get into that quite a bit here shortly. Worth noting, prior to being in service, of course, the panels must be lifted. They're tilted into place, and then they're temporarily braced until permanent restraints can be constructed. So floor and roof diaphragms, slabs on ground, that sort of thing. The panel lifting design and the operation itself really needs to be closely coordinated and be compatible with that of the engineer of records panel structural design. The engineer of record is typically not doing the lifting design, but there needs to be some clear communication there. With multi-story tilt-up wall panels, again, this is not a focus of this particular course, but there are some unique in-service design considerations. Panels can be modeled as multi-span continuous sections or as a series of simply supported spans. If you do the latter, you need to make sure that your axial force from one stack to the next is properly accounted for. With that in mind, the P-delta effect for multi-story tilt-up isn't quite as pronounced as kind of tall single-story warehouse type applications or distribution center type applications, simply because the floor-to-floor heights are significantly smaller. So always worth a mention, tilt-up is a very useful solution for structural construction. So multi-story is certainly not off the table, but our focus here is going to be on single-story construction, primarily distribution center, warehouse type, industrial type applications. The WRI strongly recommends that the ACI's PRC 551.3 tech note be part of the designer's library. The document provides some great content related to tilt-up wall panel design, and it highlights some of the common mistakes that can be made in carrying out the related analyses and design. There is a heavy focus on how slenderness effects are best accounted for in the structural analysis. An excerpt from this document reads as I've got indicated here in red. So ACI 318 design provisions for slender walls were developed from empirically derived full-scale experimental test data. Design engineers inclined to substitute alternative equations or design methodologies, even those found in some commonly available software, must evaluate whether their chosen design equations and assumptions still generally match the performance and behavior found in the experimental tests, and without unacceptable sensitivity to sudden and dramatic decreases in out-of-plane stiffness if cracking initiates. So what does this all mean? It means that properly capturing slenderness effects in the design of wall panels with long unbraced lengths is critical in deriving a safe and serviceable solution. It's crucial to utilize crack section moment of inertia in the design calculations, and we'll see that here in some of the slides coming up. Otherwise, you could end up with some unrealistically low strength level demand and corresponding deflection magnitude. So in turn, if you end up designing based on these low values, the resulting small areas of steel, steel reinforcement, would be ill-equipped to handle sudden cracking or overload scenarios. So again, the theme here is slenderness and using the cracked section moment of inertia in our calculations. So we will see that very shortly. With the previous information in mind and knowing that slenderness effects are central to the design, tilt-up wall panels should be designed based on the two documents noted here. ACI 318, of course, and its out-of-plane slender wall analysis procedure in section 11.8, and then ACI 551.2, which is the design guide for tilt-up concrete panels. So you're taking this course as a jumping off point somewhere on the WRI website. So obviously there's going to be a welded wire reinforcement flavor to it. So I feel like it's always appropriate to ask why. Why are we using welded wire reinforcement? Well, from a design perspective, And as we mentioned earlier, welded wire reinforcement is interchangeable with rebar. So calculations and equations are not really differentiating between wire or bar as the source of your steel areas. So it's you know, 6 of one, half a dozen of another from a design perspective. But the real benefit and the reason, honestly, that welded wire reinforcement exists in the first place is for the on-site advantages. Labor and installation time it can be improved upon. You know, you're reducing your labor, you're shortening your installation times, because you're putting down large areas of prefabricated steel reinforcement, and they're being placed to suit specific tilt-up wall panel geometries. In turn, the field tying of individual loose pieces of reinforcement is minimized. You know, you still have those components like reentrant bars and cord bars, trim bars, that sort of thing, but the body of the panel largely, you know, you're looking at 95% of a panel being handled with welded wire reinforcement. So it goes together much like a kit of parts. And again, it's always worth reiterating that welded wire reinforcement is very commonly available in 80 KSI yield strength. That really doesn't require any level of premium from a manufacturing standpoint. These next two bullet points really are applicable to any construction, but with welded wire reinforcement being used in tilt-up wall panels and tilt-up wall construction in general, you know, maintain an open line of communication. Designers and contractors need to be talking about the welded wire reinforcement usage in the panels. You really need to ensure that both the manufacturer and the installer, those aspects of the job, are, you know, have an appropriate level of proficiency in the area of the country in which the project is being constructed. So if that proficiency is maybe unknown at the time of the preparation of the structural contract documents, it's certainly worthwhile for the engineer to build in permissive language to give the prospective bidders some latitude to utilize the best solution for the project based on how they typically operate and their conventional means and methods. One quick mention about high strength reinforcement. So with welded wire reinforcement commonly produced at 80 KSI, there are instances in which the contractor might propose to the designer a quote-unquote value engineered alternative to the originally specified 60 KSI reinforcement. In these scenarios, the design associated with the lower cross-sectional area of higher yield strength steel should be verified as providing satisfactory strength and serviceability. Again, this relates directly to the P delta effect arising from the slenderness of the wall. If you're reducing the cross-sectional area of steel reinforcement, as we can see in the equation at the bottom of the slide, that area of steel is directly proportional to the crack section moment of inertia. So steel goes down, wall stiffness goes down, deflections go up, ultimate moment with P delta effect goes up. So it's something that has to be paid attention to by the specifier, by the engineer of record. Sometimes there are attempts to offset the effects of stiffness reduction that results from a reduced steel area. Engineers sometimes they'll try to do this in the form of an increase in the concrete compressive strength, but each case is different. You know, so the negative effect of a reduced crack section moment of inertia must always be checked, given it can still outrun the benefits gained from a concrete compressive strength increase. So there is certainly a benefit if you use a higher strength concrete, but always be checking those two, because they don't always balance out perfectly. Actually, it's rare for them to balance out perfectly. So we now set the table for walking through an actual wall panel design example. Please note that on the WRI website there is related information showing tilt-up design procedures and related welded wire reinforcement implementation. So here on this slide just shows two little excerpts of some technical blogs that we have on the website that can be downloaded for free, both related to welded wire reinforcement usage in tilt-up wall panels. So on to the design example. We're going to be using section 11.8, the alternative method, in ACI 318. We won't be covering in-plane design or lifting design or the connection design. We're really focusing on downward axial loading and out-of-plane loading, so really the out-of-plane design of the wall. Here's our typical wall panel, 25 feet wide. It's got two loading dock door openings. Loading is incurred at the top of the wall via, in this case, it very likely would be bar joists. Short little 8-inch parapet up there. Out-of-plane restraint is provided at the top of the wall via the roof diaphragm. Out-of-plane restraint at the base is via the tied connection to the slab on ground. And then, of course, panel vertical loading is transmitted to the foundation. Notice that we are going to be focusing on a design strip, or essentially in this case a wall pier that is directly adjacent to one of the loading dock door openings. Note 2, the schematic kind of vertically spanning beam we showed directly to the right of the wall panel. The unbraced length that we are going to be using in the analysis and design is 33'8", and we idealize this as a simple span. So again, we've got dead load in the form of point loads at the top of the wall from the joists. We've got roof live load from those same joists. And then we have an out-of-plane wind force that is a strength level wind pressure of 30 pounds per square foot. Step 1, excuse me, design parameters. Should be fairly intuitive. Here the panel thickness is 9.5 inches. We do have a 3/4 inch architectural reveal, so really the structural thickness is going to be 8 3/4 inches. We're going to be using 2 maps of reinforcement, one in each face. Clear cover to the vertical reinforcing wires is going to be 1 inch. Our 28-day compressive strength is going to be 4 KSI. I recognize that could be low. Oftentimes you do see tilt-up wall panel construction using 5 KSI and 5.5 KSI. It's not uncommon to use a higher compressive strength. Here we're using 4 KSI. And we are starting calculations here with the steel reinforcement yield strength of 60 KSI. Concrete unit weight, this is normal weight concrete, so it would be 150 pounds per cubic foot. The unbraced length of the design strip, which we mentioned earlier, is 33'8", and the width of that design strip is 27 inches. Note that the joist end reactions are applied at a 3-inch horizontal eccentricity from the vertical center line of the wall, so that's going to create a little bit of a flexural component at the top of the wall. So in step 2, we distribute the load to the unit strip that we're analyzing and designing. Essentially, we ratio the loads to the uninterrupted design strip. We know that we have a total joist dead load of 5 times 2.23 kips, so 11.2 kips. Our distribution width is the panel width, 25 feet. So we get a unit load by taking 11.2 and dividing by 25, which gives us 0.448 kips per foot. And then we ratio this over to the design strip. We take that value and essentially multiply it by the effective tributary width associated with that design strip. So we end up with 2.8 kips of dead load to that design strip. Similar steps carried out for the roof live load. We end up with a 3.4 kip load incurred from the joists on that design strip. And then you have self weight as well. So we take that wall dead load, take it at mid-height of the design strip unbraced length, and that gives us 13 kips. Again, that's a tributary. You note that we're taking the self-weight of the design strip itself, as well as half of the concrete over the loading dock door opening. Steps 3 through 6, this is going to be our strength check. So step 3, note that for time's sake here, we're only focusing on one load combination. Obviously, as a designer, you have the responsibility to check all relevant load combinations that are outlined in the code that are appropriate for the particular application. Here, just for this example, we're focusing on one. So here in step 3, The load combination for our strength check that we are using is going to be 1.2 dead plus 1.0 wind plus 0.5 roof live. We move on to determine the portion of the axial load that is applied with a horizontal eccentricity, so that's piece of UA. You can see we've got the appropriate load factors there, 1.2 on dead and 0.5 on roof live, giving us 5.1 kips. The total axial load at mid-height simply captures the self-weight component of the wall, so that jumps obviously pretty significantly up to 20.7 kips. The out-of-plane wind on the design strip, again, this is based on a tributary width. You can see the 1.0 strength level load factor on that wind, and we have a 0.188 kip per foot uniform load along the height of the design strip. This allows us to calculate the moment at the mid-height of the design strip that is due to the factored load and the eccentric effects. Now this doesn't include P delta effects, so M sub UA, you can see the flexural component due to the uniform wind load on the left, and then you see the eccentric moment component on the right. So we end up with a demand, flexural demand, of 27.3 kip feet. But again, this does not include P delta effects. We haven't done anything with the wall slenderness yet. For step 4, trial reinforcement and doing initial checks, we have to start with an assumption for our steel area. Here we're going to assume our area of steel is 1.25 square inches. First check, we want to make sure that minimum vertical reinforcement is satisfied. You can see the ACI reference there for that provision. We satisfy it by a good margin. Second check, prescriptive spacing. We've tabulated 3 reasonable guesses as to what we might be using to derive that 1.25 square inches. So 5 wires, 6 wires, 7 wires, and their associated center to center spacing. We then check these options against maximum and minimum spacing provisions in ACI 318, and you can see in those calculations that we satisfy both. So we're in a good range here with these options. We just need to kind of see the example through to see if we can select one of them. Check number 3. This is an important one, checking maximum axial stress at the mid-height of the wall panel. Here we're well within the limit of 0.24 KSI. You can see that we take a piece of UM over the gross area, and we're at 0.088 KSI. So we're okay here as well. And check 4, another important one. We want to confirm tension-controlled behavior always when we're doing flexural design. So we're doing that for out-of-plane moment effect, section 11.8.1.1b. We're going to assume a maximum wire size of 5/8 inch diameter, so that backs us into a D dimension of 7.44 inches. Note that the effective area of the longitudinal reinforcement, which is A sub SE, we derive per equation straight out of ACI, so we start with a true value of 1.25 square inches, but you see the A sub SE effective area bumps that up a little bit. We jump up to 1.45 square inches. We use this value in our calculations, so we move on to a compression block calculation, A being equal to 0.948. Then we can derive our neutral axis location at 1.115, all of which allows us to get to our maximum tensile strain, which we calculate to be 0.017, and of course that is significantly larger than the limit of 0.005, so we can comfortably say that this section will be tension controlled, which will allow us to use a phi factor of 0.9. Step 5, we always do want to check our phi m sub n, our design moment strength, against the cracking moment. Our phi m sub n, we're populating with numbers we previously calculated. We see that our phi m sub n, our design strength, is 45.5 kip feet. Cracking moment, that equation should look fairly familiar to you, is of course significantly smaller, 13.62 kip feet. Our phi m sub n will govern our design here. We move on to checking the moment strength against the maximum factored moment as required in section 11511B. Note that M sub U here does include P delta effect, and we are using a direct calculation as allowed by ACI 318. 318 also allows an iterative calculation option that would ultimately yield the same result. We don't need to show both methods, we're just showing the one. So you can see the equation there for M sub U. We run through this. We really have the values we need to populate that equation once we run down and determine what our cracked section moment of inertia is. So our cracked section moment of inertia is 479.1. And then we can circle back and populate that M sub U equation. Notice that our M sub U, including P delta effects, is 37.5 kip feet. So our strength check results, phi M sub n, 45.5 is of course greater than 37.5. Our original A sub s assumption is satisfactory. We assumed 1.25 square inches. So this concludes our strength check. Now we move into service deflection check. We'll handle this in steps 7 and 8. We define service level wind using the 0.42 multiplier taken from IBC. We arrive at that. There's commentary both in ACI 318 and ASC 7 that point us in that direction. Note that the reference load combination we are using actually simplifies to 1.0 dead plus 0.42 wind. It's because there is no floor live load case, so that drops off given we obviously don't have any floor loading here. So takeaway in this step here is establishing our load combination for service deflection check as 1.0 dead plus 0.42 wind. The portion of the axial load that is applied with a horizontal eccentricity is 2.8 kips. Total axial load at mid-height is 15.8 kips. These steps are really similar to the earlier steps that we carried out for strength level loading, but here we're deriving service level loads. So again, it should look familiar. We arrive at M sub SA, which is moment at the mid-height of the design strip due to service level lateral and eccentric vertical loads, again not including P delta effect. So that M sub SA is 11.54 kip feet. Keep in mind that per ACI 318, section 11.8.4.2, the maximum moment M sub A at the mid-height of the wall due to service level and eccentric vertical loads, including P delta effects, is as indicated there. So it's M sub SA plus an axial load times a service level deflection. And we'll get into that downstream here. In step 8, we do move on to iterating deflections, with a key delineation being the comparison of the maximum moment at the mid-height of the wall, which is M sub A, to a threshold that is equal to 2/3 of the cracking moment magnitude. For this example, using our previously calculated M sub A as a trial value, we see that we do in fact exceed the threshold. With this being the case, per table 11.8.4.1, the relationship for out-of-plane deflection at the mid-height of the wall due to service loads, which is delta sub s, is shown here. In the equation, note that the green checks indicate known values. First, the out-of-plane deflection, which is delta sub CR, that corresponds to the cracking moment, and of course the cracking moment M sub CR itself, which was calculated previously. Delta sub CR calculation, which is shown here, is a function of the cracking moment and gross section properties. So, this is our trial value M sub A, 11.54 kip feet, which we calculated earlier, and this is our delta sub S service level deflection equation that we'll be running through. Again, delta sub N is the deflection that corresponds to M sub N. We now move on to calculating the nominal moment strength, cracked section moment of inertia, and ultimately the delta sub N deflection that corresponds to M sub N. Note here We are recalculating the effective cross-sectional steel area, A sub SE, M sub N, and crack section moment of inertia. We're doing that based on the ACI 318 equation 5.3.1D that is modified to reflect the absence of the roof live load case, since theoretically this is the same form, quote unquote, of the strength load combination corresponding to the service load combination we just used to derive loading in step 7. So some designers will elect to use the full equation, which would include L sub R. This is of course a decision that would be made by the designer on a project specific basis. So the yellow values that I'm showing here are what we used in our previous strength calculations. You can see they're close, not precise. Some might argue that this is an extra step that might not be worth it, but I did want to go through this to show that it is sometimes done. With delta sub n now calculated, we have all the values necessary to populate the delta sub s equation and begin the process of iterating. Note that we have it color-coded here just to show the progression. So we solve for m sub a using the calculated delta sub s, and then we compare it back to the m sub a trial value. So you can see here that our starting value of 11.54 in red and our ending value of 12.43 in blue, they are of course not converged, so we move on to subsequent iterations. These iterations are shown here, and as you can see, we do achieve convergence on the third iteration. So with a converged magnitude of m sub a, we check to see if our original assumption that it is greater than the 2/3 cracking moment is still valid. We see that it is. With this established, we now have our service level deflection that we can check for conformance to ACI deflection requirements. And again, as we can see here, the service deflection is acceptable. With this completed, we have confirmed both strength and deflection requirements for our original A sub S steel area of 1.25 square inches. Step 9, we make our reinforcement selection. Any of the 3 original options would be acceptable. Recall that we based previous calculations on an effective depth dimension D using the largest wire diameter available, which is essentially 5/8 of an inch or a D31. So these wire sizes that we're showing here are smaller than D31. This would only serve to increase the effective depth, the D dimension, given their smaller diameter. So any of these will work. In this case, we will assume we're going to use 5 wires, each of which is a D25. Now let's look at the effect of a value engineer, a VE substitution, based on maintaining an equal strength of the reinforcement. So as we discussed, the original design assumed 60 KSI reinforcement. But what happens if we use an equal strength cross-sectional area of 80 KSI reinforcement, and we use that? So we set up this equality, should be fairly simple. So on the left, we have 1.25 square inches of 60 KSI steel. We're solving for the area of steel of 80 KSI reinforcement. We see that the replacement steel area would be 0.938. So instead of 5 D25s, that would be equivalent to 5 D18.8s. However, we need to compare these two design solutions. Note that the routine that you would carry out using the reduced steel area we just defined, it would be identical to what we did in the previous slides. We're just not showing it here for the sake of expedience. So this slide really shows why a cautious approach is necessary. So we have the original 60 KSI design on the left, 80 KSI alternative design on the right. Alternative design solution is still valid, but you can see that what seems like a fairly innocuous adjustment, reducing the steel area, results in a magnification of the flexural demand, including the P delta effect. So that jumps up 13% from 37.5 to 42.5. Now, luckily, Our strength utilization ratio, our demand capacity ratio essentially is still acceptable. It's still below unity. But notice how some of these other attributes are jumping up. You know, crack section moment of inertia jumps up 24%. Our surface level deflection jumps up 27%. So just keep in mind, M sub u is a function of crack section moment of inertia. That moment of inertia is a function of A sub s. So if A sub s is reduced, regardless of its yield strength, the crack section moment of inertia decreases, which in turn increases deflection. And with an increased deflection, your M sub u, which accounts for P delta effect, will increase as well. In turn, you'll have an increased demand to capacity ratio. So generally speaking, if high yield strength reinforcement is to be used, the simplest solution is to implement the 80 KSI steel area from the start. This will help avoid potential difficulty associated with validating an equivalent downstream conversion. So 80 KSI steel is certainly a viable alternative or solution, initial solution, and doing this VE approach, it is not prohibited. It just requires you as the engineer of record to go through a little bit of effort to make sure that what is being proposed as the alternative still satisfies your design intent. And I think this slide captures it pretty well. We can see some increases in values that these are not nominal increases. These are notable, and they need to be looked at. So with the design example completed, we want to jump into the type of information that would show up on the contract documents. There are really two very simple options. The first option would be for the engineer to show rebar and allow welded wire reinforcement as kind of a pre-approved equivalent. In doing this, the engineer record would include permissive language, and the welded wire reinforcement detailer would in turn take the drawing information and convert an equivalent welded wire reinforcement substitution. An accompaniment to this substitution would be conversion calculations, showing the engineer of record what the actual mathematical equivalence is, just for full transparency, as well as the illustrative welded wire reinforcement mats and shapes shown in the actual submittal and placing drawings. The other option would be just to show welded wire reinforcement from the start. Essentially, the engineer of record would treat it the same as rebar. Your focus is on sizes, spacing, and clear cover. With this, the welded wire reinforcement detailer would still be providing the submittal with the welded wire reinforcement mats and shapes, but there wouldn't be any conversion or substitution going on. And just a note down the bottom of this slide, there's really no need for a designer to worry too much about the full mat style. You can see that the 4x8, D1470, 27, 72 inches, so on and so forth. That is really a manufacturing description. All you are really interested in is, and all you really should be focused on, is wire sizes and wire spacings. The manufacturer will handle the specific layout of the mat. So seeing this in action, this is a really good example of an excerpt from a set of construction documents for a tilt-up wall panel project. This designer elected to specify the vertical reinforcement, you can see in the schedule on the right, in terms of just steel area. So there's a permission here where the steel area for, say, V1 under reinforcement mark R1A of 0.24 inches squared per foot in each face, that could be done with rebar, or it could be done with welded wire reinforcement. Now, excuse me, the horizontals, the engineer has gone ahead and specified it to be welded wire reinforcement, so it stands to reason that the verticals could quite easily be handled, and likely should be handled with wires as well. But it's really kind of a progressive approach where the engineer of record is, instead of saying a quantity of rebar or a quantity of wires for the structural reinforcement, which in this case again is all the V prefix reinforcement, they're simply defining steel areas, which is kind of a nice way to handle it. It gives gives the contractor and ultimately their vendors some options as to how to help achieve the design intent. Another example, another excerpt from some structural drawings is just to include some really simplistic language in general notes. You know, if you're doing design out of rebar and that's what you're accustomed to doing, you can certainly still do that. Including some pre-approval type language does open up the option for the contractor to explore some alternatives. So here in note number 6, it indicates that welded wire reinforcement is permitted as a substitution for reinforcing bars specified herein. There are some exceptions. Note that the exceptions listed here are really specific to very high seismic components like special moment frames and special structural walls, as well as diagonal bars and coupling beams. Those would be typically an A706 rebar. You wouldn't really be using welded wire reinforcement for those really high seismic elements. Then the second piece that is important here, if you're including pre-approval type language, is just to let the detailer know that if welded wire reinforcement, if the substitutions are being used, don't alter the reinforcement cross-sectional areas. If you want to maintain that steel area, you need to tell the detailer that right up front. Otherwise, you may be getting a substitution, a 60 to 80 type substitution. Also establish that the substitution shouldn't exceed your maximum detailed spacing. You know, if you're detailing rebar, number 4 is at 12, you don't want a substitution or a welded wire reinforcement equivalent that's using spacing in excess of that. Now, I will say that most welded wire reinforcement detailers know this, know not to exceed the detailed spacing. They've been doing it long enough, they have the experience. But it's always a good idea to kind of establish your ground rules. Note too that in note 7, it also makes mention of hook terminations being maintained. So curtailment is important. While it's not maybe as common in tilt-up wall panels, it is worth including. So if you have hooked rebar to start and you're allowing a substitution of welded wire reinforcement, requiring that those welded wire reinforcement mats hook as well is really not unheard of. That's a fairly common thing, and certainly something that can be done from a manufacturing standpoint. And then just moving on, contract documents still, it's a good idea to include a lap splice detail for welded wire reinforcement. This is kind of a lap splice detail with a kind of a quasi schedule down the bottom. The engineer kind of grouped wire sizes and then assigned lap splices based on those groupings. Note that this detail shows that the lap splice is measured from tip to tip of the adjoining mats. There is a welded wire in the lap splice region, but it is not being relied upon for any structural purposes. It's simply there to maintain the overall spacing of the wires that are going into the page. So this lap splice here is calculated using the same exact equations as if you were calculating a lap splice for loose deformed rebar. From contract documents into submittals and conversions. So welded wire reinforcement shop drawings, submittals, and placement drawings are prepared for review. Of course, the contractor is interested from a means and methods and constructability perspective. The engineer of record is looking at general conformance with design intent. You'd be hard-pressed to find a set of shop drawings, submittals, placement drawings that are simpler to review than what you will see for welded wire reinforcement. This is an excerpt of a tilt-up wall panel project using welded wire reinforcement mats. The welded wire reinforcement detailer elected to use color-coded mats, which of course jump out visually and are really intuitive. All the spacing, I know it's a very small scale here, but all the spacings and patterns and sizes are indicated on these drawings. There's a piece mark for each one of the mats, which ultimately correlates to positioning in a particular panel, which we'll see in the next slide. But again, the color coding and kind of the full-scale drawing of the welded wire reinforcement mat really drives home the simplicity of the solution. Note that every one of these mats, you can see the horizontals have kind of an extension out beyond the body of the main mat. Again, those are simply extended the way they are so that when one mat adjoins the other, there is a horizontal lap splice that is occurring. So your shrinkage temperature steel is being fully developed. So really elegant, really intuitive way to put together shop drawings, and I will say that in my own experience, that is it's a really nice advantage of welded wire reinforcement usage. The submittal process is super intuitive. Here are those same color-coded mats, just populated into specific wall panels. Again, the scale is very small, and I apologize for that, but you're taking the piece marks and then populating the wall panels, so it really does become a puzzle piece that you know, or puzzle pieces that have already been worked out for you, and so you have a kit of parts that once it's on the site, it you know, it goes into place based on this kind of color-coded solution. If there is a 60 KSI to 80 KSI substitution, you will see conversion calculations. So the welded wire reinforcement detailer has an obligation to show you how they derived their 80 KSI alternative. So this would be an accompaniment to the typical placement drawing and submittal that you would receive. Obviously, if it's straight up equal area substitution, or if you're using welded wire reinforcement right from the jump, conversion calculations would not apply. So conversions really are only going to apply if there's a you know, an equivalency that takes place using a higher yield strength material at a lower cross-sectional area of steel. You know, so welded wire reinforcement mats that are used in wall panels, they're either going to be bidirectional, which is reinforcement in both directions on a common mat, or they'll be unidirectional, which is having intuitively structural reinforcement in one direction, and those structural wires are held in a pattern by non-structural holding wires in the other direction. So here on this slide, we see a bunch of bidirectional mats, so we have reinforcement doing work in both directions. On this slide, A mat and B mat are kind of hybrids. You can kind of see where they fit into the wall panel over on the right side of the slide. So there's a portion of the A and B mat that is actually bidirectional, the portion being directly adjacent to the jambs of the loading dock door openings. So A and B mat are really, they're bidirectional. They're adjacent to the loading dock door, but then when you get beyond the vertical height of those doors, they're unidirectional, because up high, for example, you see the structural wires running top to bottom, but then you see these widely spaced wires that are really just there for holding purposes. They're just holding the shape of the vertical structural wires. The D mat that goes down along the base of the panel, this is a bidirectional mat. You can see that there's a pattern top to bottom and left to right at a fairly close interval that is doing work, obviously shrinkage and temperature and some kind of localized flexural effects. Another example, a same panel, if we look up above the loading dock door openings, we have a C mat and E mat. These are unidirectional mats, so the C mats run top to bottom, and of course you see the horizontal wires on the C mat are just, they're widely spaced, and they are just there to hold the vertical wires to shape. And then the E mat is kind of nested with the C mat, and it handles the horizontal shrinkage and temperature steel in that region. The sistering of unidirectional mats, which we see here, you know, so the C mat and the E mat is essentially sistered together. It effectively eliminates the need for any lap splices. So if you have an aversion to having lap splices within a wall panel, say lap splices associated with the shrinkage and temperature horizontal steel, the detailer certainly could, you know, kind of default to a unidirectional solution. Not a lot of engineers are that strict when it comes to the shrinkage and temperature steel, so typically you're going to see bidirectional mats used as frequently as possible, just because it's more efficient, and ultimately it would be quicker from an installation standpoint. We're going to wrap up just with some photos on the job site. You know, because of the machine-controlled fabrication of the mats, your construction administration, your CA services, which of course would include site visit observations, as well as for the special inspector on the job. Observing this material, pulling a tape, it really goes quickly because these mats are produced on machines. These are not manually welded mats. So the job of observing and validating that something has been installed in general conformance with what your design intent is it goes quick. It's very convenient, kind of low stress, and again, this is owed to the tight tolerance control on the wire arrangements that is carried out by the machines at the plant. Now, from the contractor's perspective, it's essentially an assembly line approach. The welded wire reinforcement detailer has already kind of provided the answer key for the puzzle that has to be put together. They've illustrated, so to speak, the kit of parts that needs to go together. The contractor then, they'll set up their work areas to facilitate the most efficient and timely installation of those puzzle pieces. So here the photo on the left shows a staging area. There are a multitude of different welded wire reinforcement mat types, and of course they're slated for specific regions of the form areas. You can actually see the tags still affixed to the mat bundles, and that can be really helpful, obviously from a bookkeeping and sequence standpoint. With the material staged and the forms constructed, a small crew in combination with a telehandler, typically fitted with a lifting beam, will make quick work of the operation. Again, some more photos of the installed welded wire reinforcement. I just like to point out the tidiness of the reinforcement itself. The panel reinforcement just looks really uniform, really clean, even in panels that can be fairly complex, characterized by openings and such. Again, kit of parts, these things are being laid down in mats and really tight tolerance control. And the folks that I've had interactions with on the job site, typically they say that it takes a job, it takes one project for a crew to get accustomed to putting in welded wire reinforcement and really kind of realizing its time and labor benefit. Once that project is under their belt and they've worked through kind of some of the lessons learned, they're hard pressed to want to kind of take a different approach. And again, it's just from a kit of parts standpoint, it's very intuitive. And again, we see the lifting apparatus here on the left, looking at a down the line view of the lifting beam on the telehandler. And then here in the foreground, another really nice view of the welded wire reinforcement layout, just showing how uniform it all ends up being installed. So that really wraps up the tilt-up wall panel content. For more information on general design, detailing, and construction related to welded wire reinforcement, please visit the WRI website. You'll have access to a multitude of free technical publications, articles, and calculators. Everything on the website is free to download. So thank you very much for taking the time to watch this WRI Continuing Education course. Please proceed to the quiz linked below if you are seeking continuing education credit associated with maintaining your professional licensure. If there are any questions about the content presented today, please reach out to us on the website or at the email address noted here. Have a great day.